it's a pleasure to be back. Yes, well, gamma ray bursts I find to be a very difficult topic to talk about simply because there are so many neat observations that need to be explained, and it's hard to fit everything in 1 hour. And I can never resist the temptation to cram as much in as possible. So I apologize in advance. But I will try to dwell on a few things that I think are fundamental. Well, there are a lot of puzzles and apparent paradoxes in gamma ray bursts that make the topic so interesting. One is, and this is an old question, this is the reason people had so much trouble believing that gamma ray bursts were at cosmological distances, simply that the amount of energy you need to produce that much power requires so much mass that it would totally obscure whatever is being released. It's kind of like big stacks of firewood making it impossible to see a campfire. But it's even worse than that because particles radiate photons on an individual basis, and the photons are thoroughly embedded within the matter at the time that they're released, and they have to make their way out of the baryons that emitted them in order for us to see them. And that in itself, if you work out the numbers, they should not be able to do that by any means. And to make things even more puzzling, the spectrum almost always peaks at several hundred keV. If there were different amounts of baryons or different mixtures of photons and baryon ratio, you would expect different amounts of adiabatic deceleration of the photons and variation in the relative content between the baryons and the photons. And you don't see that. You see mostly photon energy, and it's always with the signature spectrum. This is very difficult to explain. Whoa, wrong button. This is very difficult to explain with optically thin synchrotron emission because the peak energy is so extremely sensitive to the various parameters that you could put in. For example, it's sensitive to the bulk Lorentz factor to the 4th power. And that can, since the bulk Lorentz factor can vary by a factor of 2 easily, it would be hard to understand why it always peaks so reliably in the same place. And for a while, people thought that might be a selection effect. Well, the instruments that we use are designed to look in that spectral region, but it turns out that that's not the case. That reason doesn't hold water anymore. Now, another thing is, as I'll show in the gamma ray burst prompt emission seems to exceed the energy in the blast wave that results from it. And sometimes by a factor of 100. And here you see some of the data. This is an old slide, but it continues to look like this as more points pile in. You see that the apparent prompt emission relative to the inferred energy in the blast wave, which admittedly is just an estimate, it can be as low as 20 or 30% in a couple of cases, but mostly it's above 1, and occasionally it's 100 times as much energy in the prompt emission as there is in the blast wave. And
is this corrected to beaming? Or
now, I've plotted as a function of peak energy here. I'm going to argue in this talk that the peak energy and the prompt and the energy in the prompt emission can be functions of viewing angle. And if I make the viewing angle correction and redo and replot the slide, you see that it has far less scatter than before, which already tells you something. It tells you might be doing something right if anytime you can reduce the scatter. And then the value is typically between 5 and 10, but again, as much as several hundred. And what you would expect, say, from internal shocks, like within the blast wave, would only be a small fraction of the total blast wave energy, because you expect the energy and velocity fluctuations not to exceed the total velocity. So what you would expect from internal shocks is down here, and what you see is up here, and occasionally beyond. But let me emphasize what I think is the most important point of all, is that the scatter seems to be upwards rather than downwards. If there's a ragged edge, it's on the high side, not on the low side.
Could I just check?
Yeah.
You have reliable estimates of the solid angle of the gamma ray emission?
No. No, I don't, and I don't have reliable estimates of the blast, but it's per unit. It's per unit solid angle.
You're using
Because it's just a ratio, and yes, they may have different angles, and that's going to be the topic of.
That's not the correction plotted here.
What's T90 and how do you estimate it?
T90 is just the duration of the burst, and you see that the duration of the burst can vary a lot, but it doesn't seem to have any influence on the.
It's the time over which 90% of the gamma ray photons are emitted.
And while we're at it, I don't understand the units in the vertical axis.
That's understandable because I haven't explained them yet. I've just said that I made a viewing angle correction.
And how do you make the viewing angle correction below solid angles?
I hope to tell you in this talk.
Oh, okay. Good.
I just want to again emphasize here that if photons were trapped in the baryons, and their main challenge is to fight their way or work their way out of the baryons so that they can be seen, and the main problem is adiabatic losses, you would expect there to be a lot of scatter down here if the baryon content varied by a factor of that's typically expected in astrophysical uncertainty. Now, again, if it doesn't seem to me that the blast is making the gamma rays. It seems to me that the gamma rays are accelerating the baryons, and that the gamma rays are the primary source of energy, and that's going to be important.
What if the free energy is magnetic in Poynting flux?
Then you have to convert it to gamma rays.
But you wouldn't see the blast. You wouldn't necessarily see a large blast.
No. When I say blast energy, I mean in the baryons. In the baryons. Electromagnetic energy is electromagnetic. Yeah. Now, another thing that many people were surprised is that afterglows, many afterglows have flat intermediate phases, and I'll show you an example of that. Here is an afterglow that doesn't have much of a flat phase, maybe a little bit here, but you see it connects almost smoothly to the prompt emission. It seems like a natural extension of whatever's making the prompt emission. And energetically, or at least energetically, it's matched. The the energy released in the afterglow is comparable to the energy that was released promptly in photons. And here's an example, a case where it looks like it should have connected, except that there was this long pause, a lull, and it took many hours, a significant fraction of a day to actually get its bearings. And what was going on here? Why was it missing? Now, another question is why the Ahmadi relation among long GRB? Why is it an inequality? Why is it true for long bursts but not for short bursts? And why do so many short bursts, for which it's not true, why do they have long, soft X-ray tails, for which it is true? The long tails obey the Ahmadi relation, but the short, hard emission that we used to think defined the short, hard burst does not obey the Ahmadi relation. Okay, now here's the Ahmadi relation. It's basically the Hertzsprung-Russell diagram for a GRB. It relates the total energy output in the burst to the spectral peak. And you see that very bright bursts have the harder spectra, and there are very soft gamma ray bursts, which really aren't gamma ray bursts. They're called X-ray flashes. On the one hand, they seem to connect up. They seem to be the same phenomenon. And it's evidence that you can detect X-ray bursts. When I said that spectra always peak at 2 to 300 keV, I mean that was an exaggeration. You can see other spectral regions if you have the right equipment, but they all line up either on this line or to the upper left. They're about, this is an old slide, by now they're about 150 GRB with known redshifts. And I think without exception, they're all either on the line or some of them lie off to the upper left. There are none down here. Now here again I want to ram this point down throats. The absence of points to the lower right of this line, to me, is truly amazing. When X-ray flashes were first discovered, people said, well, naturally, they're dirty fireballs. They're fireballs that happen to have so many baryons that there was a lot of adiabatic cooling, and most of the energy went into the baryons. We didn't see that in the afterglow data, and we don't see it in the prompt emission data either. This line here is what you would get from dirty fireballs because it's a contour of a photon number. Anything along this line has the same number of photons. What the Ahmadi relation is telling you is that the softer the photons, the fewer of them that you have. And you have them, and they're fewer at least in proportion to the energy, maybe even more so. Maybe even the higher power of energies. And they just ain't dirty fireballs. I won't have time to discuss the one possible exception to that, but it's an exception that's so weird that it proves the rule. And the absence of dirty fireballs, to me, suggests that the lack of baryons is simply a non-negotiable, cut-and-dried issue. It's not a sliding parameter that you can dial. To first approximation, there aren't baryons. And that's, I think, going to be the main point of this talk. There are a few, but they're incidental. Okay. I mentioned that the short hard bursts have X-ray, the soft X-ray tails that are as long bursts, and that they too obey the Ahmadi relation. Well, here's the data. I made the claim. I owe you the data. So there it is. Now, what's the difference between short and long bursts? And why is the distinction not perfect? They do overlap somewhat. And the question is, should we be wondering about what's different about them, or should we be wondering why they're not more different? Why there's this almost numerical coincidence between their durations? It's generally thought that long bursts come from collapsing massive stars, and short bursts come from merging neutron stars. But nobody's ever explained to me why merging neutron stars would take less time to release their energy than collapsars. I mean, if anything, they should take longer because they have more angular momentum to shed, and the collapse is less spherical. So what, deep down, what is the difference? And one more thing, the spectrum in gamma ray bursts, and even the pulses within gamma ray bursts, tend to soften with time. They start hard and they get softer. And the time it takes to do that inversely correlates with gamma ray burst luminosity. But that's only for the long bursts. The short bursts and the ones that are associated, the low luminosity ones that are associated with supernova, are not on that correlation. And I'm sorry for the low quality here, but this is the spectral lag versus luminosity on the y-axis. You see, for long bursts, there is this inverse correlation. Short bursts and low luminosity supernova-related bursts in green are in a different place altogether. So why? All right. Those are some GRB puzzles. And there are a lot of them. And OK, so what about solutions? Well, why did the baryons not absorb most of the energy? Well, there are two possibilities that have been suggested. One we suggested is simply because gamma ray bursts emerge from magnetic field lines that thread an event horizon, and there's no way you can get charged baryons onto those field lines. Let me show you a picture of that. You can have the super Eddington luminosity, and when I say super Eddington, I mean like 15 orders of magnitude super Eddington. It can drive a wind off an accretion disk, and I say that it would, but the magnetic field lines that connect to the black hole are going to be totally clear of baryons. You can have neutrons leaking across, and that can actually be significant and have interesting observational consequences. But otherwise, you have general relativity provides us with a neat, clean way of keeping things baryon-free. And it's not clear to me that we could have gamma ray bursts without event horizons. I'm not saying I can prove it, but it's something that personally motivates my own research on the matter. Now, another possibility was suggested by Martin Rees and Mazaros is that the energy does go into baryons, just like a supernova, but because because the bulk Lorentz factor is so high, the energy is reclaimed and dissipated by shocks at large optically thin scales. And Martin Rees is a very popular guy, and this explanation was taken very seriously. And I have to say, I have no problem. I take it seriously too. I certainly agree that that's what makes the non-thermal photons, which vary greatly among GRB. There's no typical spectral peak. There's no Ahmadi relation. Non-thermal photons typically vary from one burst to another. They at one time it was thought that most of the photons were non-thermal and that they all came from shock-accelerated photons. I think with the LAT detections and the calorimetry done by the Fermi Observatory, it's now been established that the non-thermal photons are typically 5 to 10% of the total, and the rest is this rather thermal-looking peak. But again, in order to do this, you still need very few baryons because you have to get to Lorentz factors of several hundred to make this idea work. And the question is still, why would you have few enough baryons even for this possibility? And again, why would the spectrum typically peak in the same place all the time? There's no, you can't even, it doesn't even fit optically thin synchrotron emission. It's too, the lower energy slope is too steep in many cases. So I think the problems with this are widely recognized now, and I think it's also fair to say that Martin Rees has always liked the idea of baryon-free photospheres, and actually wrote some papers on. Now, but this, of course, is clearly the case for supernova. If you have a super Eddington energy release, you get a blast of baryons shot off into space, and I'm sure that happens with gamma ray bursts too. It's just that's not the thing that's the gamma ray burst. So let me continue with this. If you're going to sell your soul to event horizons, you better be prepared to live without baryons. If there are no baryons, then photon entropy can be increased only when there are pairs. And that means that the temperature decrease due to entropy increase. Photon entropy increase simply means that you're making more photons, and that there will be less energy per photon. But if the temperature goes below that needed to sustain pairs, it just means that the pairs annihilate. There's nothing else stopping the photons, and they just get automatically released. When the temperature in the rest frame of the pairs, it goes below about 30 keV. And given that they may have already started expanding and will have a significant bulk Lorentz factor, this agrees nicely with the spectral peaks being consistently at several hundred keV. That's one thing that's nice about this hypothesis, is that it automatically releases its photons when the temperature drops much below the observed spectral peak.
So there's no gamma factor that shifts that up?
Well, there is. There is. Because since the compactness parameter is so large, you only need a very small fraction of the quantity pairs, like 10 to the minus 10th or so, to trap photons. So you want the Boltzmann factor to get below 10 to the minus 10th, and that means 30 keV as opposed to 1 MeV. But still, 30 keV for something that's expanding with, if anything, the Lorentz factor you need is only about 10, which is embarrassingly low, unless you say, oh, let me just skip. Unless you say that the photosphere is still accelerating at the time you see it and will eventually get to a high enough gamma to explain all the other things you need, like non-thermal photons with very fast time variation. I know. It's hardly surprising that it should be accelerating. It's not a big. I'm just saying it because, for some reason, much of the world has come to the conclusion that we're seeing photospheres at the terminal gamma, and I'm just saying here that doesn't work so well. I would. Not 100% sure. My inclination is that it's still accelerating at the time you see it. And that will prove to be significant.
So you're creating the pairs by photon-photon collisions.
Or other things that are more exotic, but yeah.
But if the rest-frame radiation temperature is 30 keV, you're not going to make many pairs.
No. Originally it was higher.
Okay.
But it's expanding.
Yes.
As soon as the expansion lowers the, say by adiabatic cooling, as soon as it lowers the temperature below 30 keV, the photons are released without further entropy and without further adiabatic losses.
But you have enough pairs to make it optically thick to make the photons relax. Yeah. Okay.
Initially,
Yes.
you have. Not just to say that you have enough is an understatement.
Okay.
You have enough by 30 orders of magnitude. And then they have to expand, cool, annihilate. Okay. Now this has to happen at what by gamma ray burst standards is fairly small radii, about 10 to the 11.5 centimeters. Because it's hard to sustain a lot of pairs well beyond that. It's hard to sustain a high enough temperature much beyond that because it's just too much energy, it's too big. And this means that it may occur within the host star, this photosphere. And that's also significant. So just to review, the hypothesis that I'm going with here is that the primary output of GRB is gamma rays in pairs. The typical photospheric spectra, as seen by the observer, are of order 1 MeV. The record is 4 MeV, but let's say somewhere between 1 and 4 MeV. And that the diversity of spectra and fluences and observed durations and maybe even the light curve profile is mainly a function of viewing angle as opposed to the intrinsic central engine. And the non-thermal photons, indeed, I attribute to baryons loaded downstream of the central engine. It could be neutrons leaking in and ionizing within the fireball, or it could be baryons that are in the host star that just never managed to get out of the way, and they got plowed up. Okay, so here's a picture of a fireball accelerating within a host star, and maybe it's going to pick up some baryons at the surface of the host star or slightly beyond, or maybe from a wind that's coming out at the walls here, which I didn't draw. Well, what did various observers see? Observers 2 and 3 are not going to see anything because by the time it gets out of the star, the relativistic beaming cone is already too narrow to be in their direction. Now, observer 1, what is he going to see? Well, I try. It depends whether he's just outside this baryons blocking or just inside, and I'll elaborate presently. Just to review special relativity, this is what this is what you see when you're viewing something from an angle. In other words, suppose the fireball is isotropic in some rest frame, but that the Lorentz factor beams it not quite in your direction. So you're a little bit off to the side. What exactly do you see? Well, just to fix the ideas further, suppose that the photon is coming from the central engine. It scatters off a baryon that somehow managed to get in the way of the flow, and then into the path of the observer. Okay, the important thing here is if everything is moving ultra-relativistically in this direction, what ends up going towards the observer is actually going backwards in the frame of the scatterer. That's of utmost importance. For example, we cannot see the dark side of the moon. But if the moon were being shot at us at ultra-relativistic velocities, then we could see most of the dark side of the moon. And it's just that you see it, you see the scattered photons greatly softened because in this rest frame they were redshifted by a factor of gamma, and then they're blue shifted by a factor of 1 over gamma times 1 minus beta cosine theta. But if you're outside the 1 over gamma beaming cone, the photon will look a lot softer than the original photon from the central engine. And that's even though it made an elastic scattering, the scattering surface. It's simply it's not Compton recoil. It's even, this is assuming Thomson scattering, but the observer off to the side sees it much softer. And if there's no obstruction and it's accelerating, you'll see it getting brighter as long as you're within 1 over the gamma cone, because as it's beamed forward, it gets much brighter as the beaming factor, as it becomes more beamed. But as soon as the beam becomes too narrow to encompass your line of sight, then you start to see it getting dimmer and softer very quickly. So if it's accelerating until gamma equals 1 over theta, the GRB gets brighter with more or less constant spectrum. Then after that, it gets softer and dimmer with the apparent temperature of the photosphere diminishing as t to the minus 2/3. And that's exactly what the observers report. When a gamma ray burst has an identifiable pulse, they can have a lot of different pulses within one event, but if you see one subpulse that has a nice coherent history, it gets brighter. It turns on very quickly. The apparent temperature stays constant, and then it gets softer and decays and the temperature goes as time to the minus 2/3, and that's exactly what you expect. So here's a picture. Well, now let me move on to a different topic. Imagine that this is the beaming cone and that you're an observer off to the side slightly. And here I show different observers being off to the side by different amounts. Each one at any given instant is going to see a progressively softer peak and with much lower fluence. And if it were a point source, the E ISO would go as the spectral peak to the third power. That's just the way it works out, because this Doppler factor, oh, this continues down here. The received power goes to the Doppler factor to the fourth power. E ISO is proportional to the duration, which goes as 1 over d, so it's only 1 over d to the third power. But now here's the thing. If you're seeing energy from an extended source, that's many different point sources. So, here's an extended source. This guy is seeing contributions from a solid angle that's proportional, well, that's about as big in diameter as his own offset. So he sees the number of the solid angle that contributes considerably to what he sees goes as 1 minus cosine theta, which is approximately 1 minus beta cosine theta, and that gives you one more factor of cosine theta. So actually, E ISO is roughly proportional to the square of the peak energy, and that is the Ahmadi relation. So you can account for it just by saying that, well, the line of equality can be accounted for by saying that all these observers are seeing an extensive beam with a finite solid angle, and they're just a little bit off to the side. If they're a lot off to the side, or if the beam is a pencil beam rather than an extended beam, then they'll be in the upper left. And there are outliers, and short gamma ray bursts are also in the upper left. But there's never going to be anything here. And that, to me, is the best answer for this Ahmadi relation, that anytime we're seeing an X-ray flash or a softened burst, we're actually seeing much fewer photons, because we're seeing we're seeing radiation that was emitted backwards in the frame of the emitter, or in the frame of scattered backwards in the frame of the scatterer. And if we had seen it before it was scattered, it would all be up here. It would all be hard. And what I'm really, it would be a lot easier to see into a black hole if there weren't a lot of other things getting in the way. But what I'm trying to do is to unravel the processing that we're seeing, and it fits the data if you say that that gamma ray bursts are seen by observers who were just off angle from the direction of motion of the emitter or scatterer. And
What happens if you're on axis?
That's a very good question. If you're on axis, you might see this. You would be at the very high energy end.
Why couldn't it be in the corner on the right?
What?
Why couldn't it be in the lower right corner?
The lower right?
Yeah.
Because gamma ray bursts all have a lot of energy, and down here they would have a very small amount of energy.
Right, but you beam the radiation accessible.
No, but the vertical axis is the spectrum, and I'm saying, oh, right. I'm saying that the reason that the spectrum has to be of order in MeV is that you're seeing a pair annihilation photosphere, ultimately, after you account for all the viewing angle effects. And a pair annihilation photosphere is not allowed to be too soft, because the pairs would have been annihilated and the photons would have been released before they had a chance to get soft. Okay, and the intermediate flat phase of Afterglow is just that. In the early stage, the observer is slightly out of the beaming cone, but later, as the blast wave slows down, the Lorentz factor decreases. Suddenly, the observer finds himself inside the beaming cone, which is where classical afterglow theory becomes operative. And until then, he didn't see the afterglow. And the flat phase of afterglows that Swift discovered, it came as a surprise to a lot of people. I'm fond of, I actually have been guilty of boasting that I predicted it, because this paper was submitted before that discovery was announced. I was reading it. It turns out that what inspired this paper is, apart from my own theoretical expectations, was that in the Beppo-Sachs data, they had discovered in the very early stages, when they had succeeded in catching an afterglow after 70 seconds, they noticed that there was a lull in one particular case that they attributed to just whatever, just low efficiency. It just didn't happen to be an internal shock or whatever. And I pounced on it, and I suggested that it was because we were slightly off to the side, and it took 200 seconds, which was considerably longer than the prompt emission, for it to slow down just enough to be in our to encompass our line of sight. And but I certainly expected there to be lots more like this at the time, and I even told people that if they didn't observe this, I would just shut up. But after they were discovered, we wrote another paper that fit the flat phase with simply the combination of prompt emission plus a delayed onset of the afterglow, and it typically looks like a flat phase. But really, it's just the sum of prompt emission that's nosediving here and afterglow that's turning on. Okay, what about short GRB? How am I doing with time? Do I have time to discuss short GRB? What?
10 minutes or so?
10 minutes. Okay, I'll talk fast. But basically, let me see if I can jump to a picture. Yeah, we said that in the early stages, when it's just accelerating, observer at angle 3 would have seen it had it not been for the stellar envelope obscuring it. If there were no stellar envelope, in a nutshell, he would have seen it. But he would have seen it at a much earlier stage when gamma was much lower. When gamma is much lower, the spectrum is softened much less. In fact, let me put it this way. When you see something accelerating at you, it gets brighter and brighter until the gamma is just 1 over theta, which is theta is your viewing angle. At that time of maximum brightness, the spectral peak is always half of what it was at the central engine. If it was 2 MeV at the central engine, it's 1 MeV at the point of the spectral peak. And then it gets softer. But obviously, if you see it earlier on, it takes less time to the acceleration time scale is shorter, and the whole process will take less time, and you'll see harder photons. Observers 1 and 2, well, actually observer 3, if there is an envelope, he only sees it after it escapes from the star at a later phase, and then he sees a softer spectrum. But if there's no envelope and the guy happens to catch the hard burst, he will see a harder spectrum than if there had been an envelope and he had to wait. And that's why short bursts are harder than long bursts. On the other hand, if he'll still continue to see the long, soft X-ray tail, even if it is a short, hard gamma ray burst, which will take just as long. And the long, soft tail will, because it's governed by relativistic kinematics, will obey the Ahmadi relation. All right, I'm gonna talk quickly, but basically, observers 2 and 3 can see, they see an X-ray, a short hard burst and an X-ray tail if there's no envelope, and they see an X-ray flash if there is an envelope. And the difference between short gamma ray burst and the difference between short gamma ray bursts and long gamma ray bursts is the existence of a host star. Merging neutron stars are not, they don't give a central engine that's necessarily so different from a collapsar. It's just that they don't have a large envelope that's obscuring the early stages, and then you're more likely to see a short burst. Because it has a larger solid angle, it's intrinsically dimmer. You'll see short bursts up closer, and there'll be fewer of them. But among the close sources, you'll see more of them because the solid angle is larger. Again, I'm going to skip the. There's some really good stuff here that I'm skipping, but now there's still some nagging problems, and why are most of the observers close to an extended source but not on it? I mean, if you go all the way back to that picture, you would think that the actual beaming cone takes up more solid angle than the observers who are very close to it. And not only that, but people are now pouncing on supernova at very early stages and analyzing light curves, and they're inferring that there are extremely thick winds that are emitted perhaps a year before the supernova that should totally enshroud gamma ray bursts. I mean, if this is typical, then why do we ever see gamma ray bursts? And also, why do most observers see softened gamma rays and only a minority of them seeing the fresh, hard ones? Well, again, what about all the observers who should have been in the beam? Well, one thing you could do is to make this sort of shaped like an amoeba, so it has much more perimeter and less solid angle, and then you can get lots more observers just off the edge. But but you wouldn't solve this problem. I talk a lot about all these afterglows, like 50 or 60% that have flat phases. What about the 40% that clearly do not have a flat phase? Why don't they all have spectral peaks in excess of 1 MeV? Well, now I'm going to argue that even if you were here, inside the beam, you still would see it softened. And that's simply because this beam here may be cloaked by an optically thick shell of baryons. And again, you may not be able to see the front side of this cloak. You may only be able to see the back side, which is facing the black hole and is evacuated of baryons. And I simply suggest that that if the observer who is inside the cone is simply going to be there's simply going to be this dead zone of eclipse where he can't see it, but he can see emission from radiation that's bouncing off the periphery. And here, let me just show a picture of something plowing out of a host star. And here you see time evolution. It gets closer, and finally it breaks through. But it still has plowed up some of the envelope, which is acting as a cloak. And looking at it up close, imagine that gamma rays are streaming through an optically thin region here. They bounce off the cloak, and they scatter backwards, but not exactly backwards. When you make the Lorentz transformation for radial motion, you get photons that's aimed at the observer. But again, since the observer could only see, well, let me put it this way. Had the photon scattered right here, had it been coming straight at the observer, there's no way it could have scattered in the direction of the observer. It has to have hit off to the side and scattered off material that's not moving exactly at the observer. So you still have a situation where the observer is in the primary beam, the 1 over gamma beam, but nevertheless he's only seeing material that's moving slightly off his line of sight, not material that's moving exactly at him. And that's why, well, I'm going to skip ahead and then go back. But that's why you don't see more photons that are very hard, because even if you're in the line of sight, the optically thick cloak means that you're only going to see softer photons. Now, just a second. If you do the math, you know, photons scattering backward, don't they still have to cross the shell to get to the observer? Well, the answer is yes, but by the time they do so, the cloak may have already been optically thin. And if you do the math, you get reasonable estimates that the minimum offset angle you need is about 1/3 of 1 over gamma, which means that you'll see most URB at 300 keV rather than 3 MeV. 5 minutes? 3 minutes. OK. So let me just show you a picture of this shell. If you really did it right, it would be corrugated, because it would be, if it's accelerated, it would be Rayleigh-Taylor unstable. And what would it look like? Here's something that could happen. The observer is in the shadow of an optically thick cloak, but the cloak is accelerating, and it's actually a finger in the cloak that's accelerating fast because the Rayleigh-Taylor instability is making it poke out. As it accelerates, the observer is still in the shadow. And it accelerates even more, and the observer suddenly is not in the shadow. He suddenly sees gamma rays, but they turn on very quickly. And here's data. This dotted line, which is not the data, is what it would look like if it were optically thin. But here's what it looks like, and this is the data if it's optically thick. So here's an example of an observed pulse that we think were blocked by high optical depth and switched on just when gamma accelerated to beyond 1 over theta. Okay. One more interesting thing, the Caltech group reported an afterglow without a GRB. Maybe it was a very obscure GRB. And in which case, further searching will find more such objects. And that, I suppose, is a prediction. What about a GRB without a giant host envelope? There are sure GRB. Almost all of them are seen off to the side because that's where the solid angle is. But occasionally, you should, maybe once in the blue moon, you should just happen to be in line with a naked GRB, and it looks very powerful, like a long GRB, but there are very few baryons. My candidate for that is a particular GRB, 090510. It was the brightest short GRB ever observed. And here's the thing. Its sustained afterglow should have been one of the brightest, and yet it was one of the dimmest ever observed. Because even though it started off very bright, it pooped out after 1,000 seconds. And that's the signature of something that just doesn't have, it has a lot of energy but very few baryons. So all this supports the idea that the cloak that is usually provided by a giant host star envelope both softens the spectral peak and stores the energy for a sustained afterglow. And that it wasn't really part of the fireball at its inception. I'm going to skip the part about neutrinos, but the idea is basically that if there are gamma rays, they're totally cloaked, and we don't see them, they should still be neutrino sources, and maybe they're the best neutrino sources. So if you ever hope to see gamma ray neutrinos from gamma ray bursts, the fact that it hasn't happened yet doesn't quite rule it out. So my conclusions, and I have 1 minute. So that's perfect. If you drop the commonly made assumption that the velocity of the most strongly contributing emitting material coincides with the line of sight, then many GRB puzzles fall into place. And it doesn't take much of an offset because the Lorentz factor is so high. So we're talking, everything is on a very small angular scale. The difference between the velocity of the last scatter and the observer could be because the baryons enter the jet downstream in patchy fashion and the perimeter of the emission is corrugated. Or it could be that the last scattering is at the inner surface of an optically thick baryon shell. So the last slide is that simply gamma ray bursts are consistent with the interpretation that the fireball starts off without baryons. If there were no afterglow and no cloaks, this conclusion might have come even easier. But life is never that simple. It's been 20 years of unraveling, but I still claim that this interpretation gives a great phenomenological account of all of the complicating things that we did see. And even the fact that the photosphere is accelerating as we see it also makes a lot of puzzles fall into place. And thank you again.